everybody. This is going to be homework 3A1. You can read from the title. And this, what we'll be doing is we are going to be deriving the amount of heat that needs to be added into our reversible reaction, or reversible equation, equation, in which it is an isothermal, reversible compression. And these are the three things you want to hit while going through this derivation. So first, what we want to do is look at our first law of thermodynamics, in which the internal energy equals the heat added I know you won't be able to read this. This is more for my frame of reference than yours, because I'll be speaking it out for you. And then this is the work done on the system. And because this is reversible, what you get from this is that the work done on the system, or let me back up real quick, that the pressure on the outside of the system equals the pressure on the inside of the system. And so the work being done on the system would be the pressure. And what we know in our, actually let me draw a little box here to kind of symbolize this. What we know is that isothermal, which means temperature is kept constant, and reversible, which P in equals P external. Okay, and now we want to compress our system. And so what we know from our inside of our function is that it's an ideal gas. And so PV equals RT. Again, everything we're going to be doing today is with 1 mole. And so just keep that in mind. It's per 1 mole. And so we would have that our pressure external, let me rewrite this, we would have du would equal dq rev, then we subtract, let's look, if this is going to be pressure, this would be RT over V. So it would be RT over V. And this would be per change in volume. I would believe, let me think about that. Yes, per change in volume. And so now we have internal energy with our heat added, and the work done on the system. But our internal energy can be written as CV dt, or the heat capacity multiplied by the change in temperature, equals dq rev minus RT over V. Oh, I just got chalk in my mouth. That's disgusting. Over V dV. And so what we know, as if this is isothermal, the temperature is constant, which means our change in temperature will be 0 or zilch. So we can go like that. And then what we end up getting is we have dq rev equals RT over V dV. And from here, what we can do is we can integrate our function. We can integrate our function. And so what we would get, because this is dq, so it's already in its derived form in here. So we would derive this side in terms of our heat added, and we would derive this term in volume. And so, actually, in volume, yes. So let's do that. And so we would then derive it. Actually, let me write my integral here, and then I'll carry it over. So we would have the integral of 0 to the heat added reversibly, and then the V1 to V2. And from here, RT would be constant. So we could take that outside. And so what we would end up getting is we would have, draw a line, we would have big Q reversible equals the, okay, now we're going to have RT And so what we would have over here would basically be 1 over v dv, which we know as the natural log. So that would then be ln of v2 over v1. However, because it is a compression, we know that we are going to actually have to cool our cylinder or our system if we want to keep the same temperature. And another way of showing that would be to keep this negative sign out here. Instead of taking it to the other side, we want to keep a negative outside. And so when we would do that, we would end up with, there's not enough room for that, so let me just erase something real quick. We would have dq rev, or q rev equals negative RT ln of V2 over V1. But what we know of V2 and V1, if we're going to compress it, and up here, as I didn't allude to this earlier, but I wrote it down up here, that V2 equals V1 over 2, is that we would end up getting, oh, wait, no, that's how you get the negative sign out front, excuse me. Yeah, let me get rid of that. So the negative would be to take this across. I was just mixing up my signs here. V2 over V1. And if we know V2, let's do this over here, or let's just do right here. We know it would be ln of V2, which we know to be V1 over 1, or V1 over 2, and then we would divide by V1. So what this would end up equaling would be the ln of 1/2, which, if you don't know from the graph of ln looks like, it looks something like here's a point of 1, it crosses. And so anything past 1 or less than 1 would be negative. And so what we could do is we would have Q rev equals the negative of RT over, or multiplied by the ln of 2. As the ln of 2 and the ln of 1/2 are not interchangeable, but they are, one could say they're reversible, as long as you have the negative sign up front. And so what this proves here, as R and ln of 2 would be a constant, that from whatever the temperature is, when we want to compress it by a certain amount, that our heat added has to be negative. And so we are actually having to cool down our system to do this type of work. Now we'll be doing question A2, in which it asks us to describe the pressure, volume, and the pressure temperature relationships in a adiabatic reversible compression / expansion problem. And so we're going to start off the same way we started last time with the second thermodynamic law, which is du, or the internal energy, equals dq rev, as this is a reversible, or the heat added, plus the work done on the system. But what we first, not but, so what we know is that the work done on the system, as it's a reversible expansion, is that the P in, or not pressure, yeah, pressure inside equals the pressure on the external, which means that us over here, it is on the inside, the pressure is an ideal gas, or it's ideal gas-like, so we can use PV equals RT. As again, for this problem, what we are going to be doing is assuming N equals 1. So anything that where you would think, oh, the moles wouldn't cancel, everything here is on a per mole basis. And so let me get back to this. We would have, as this would be pressure, we would have negative RT over V. And if we know that dq rev, which is the amount of heat added, also known as the heat you could transfer, would actually be 0. As for adiabatic, which would mean it's well insulated, there would be no heat transfer. So we would call that 0, and it would then end up equaling what we know the internal energy to be the heat capacity multiplied by dt. And so heat capacity, yeah, multiplied by dt. And what we've learned in differential equations along with this class is you want the right variables to be on the correct side. So as you see over here, we have negative R times T over V. And over here, we have the heat capacity multiplied by the change in temperature. And so what we want to do is take the temperature over to this side. And so what we're going to do is we're going to have CV, which is a constant, multiplied by dt over T, which then equals negative R times 1 over V. And one thing I forgot to mention is this is on a dV, as this would be dW, and we're going to change this to dV per change in volume. And so then this would be dV. And now we're going to integrate from T1 to T2, and then integrate over here. Actually, and we're going to integrate from V1 to V2. And what we would have over here is we would have CV multiplied by the ln of T2 over T1. Okay, this is just a simple integration. I'm just going to make sure you can kind of tell the difference where one starts and the other begins. And then that would equal the negative R. Actually, let's keep the R and the negative signs separate. So we would have R multiplied by the ln, negative ln of V2 over V1. But what you can do with this negative sign is flip the insides of the ln. So we would then have, let's exit this out, this would then equal R times the ln of V1 over V2. And now let's take R to the other side so we have our volumes separate, as you can do some other things with those. So now we would have CV over R, as these are the constants, multiplied by ln of T2 over T1 equals the ln of V1 over V2. V1 over V2. And what you want to do from there is you want to get rid of this ln. This ln is annoying. And so what we would do is we would take it to the power, or not take it to the power, we would raise it to E. And what raising it to E would do is it would have us T2 over T1 to the power of CV over R. Okay? And then that would equal V1 over V2. And from here, you can mess with the powers. So from getting T2 over T1 to the CV power over R equals V1 over V2, we're going to have to take a step back and rewrite T2 and T1. So over here, we're going to rewrite using PV equals RT. We're going to write T2 equals PV over R. And it's going to be specifically P2 and V2. As again, this is important to make sure you're using the right, not number, but make sure you're using the right condition of pressure or volume. And now we're going to have T1 equals P1 times V1 over R. And something that's important to look at is, so what we have over here is T2 over T1. And if we were to do that over here, T2 over T1, the R would cancel. They would flip up and cancel, which would leave us with P2 multiplied by V2 over P1 multiplied by V1. And now we want to put this into our equation that we have, our equation we've derived so far. So we would have P2 over V2 multiplied or divided by P1 times V1 to the power of CV over R equals V1 over V2. So now what we want to do is we're going to separate our variables or separate our powers. So what we would have is we would have P2 multiplied by, let me look at this real quick. Now we can have P2 of CV over R multiplied by, we want to take V2 over to the other side. Or you can think of this as moving this over. So we multiply that by V2, then we would have CV plus R, because if we have an extra power, to move it to the other side, we're going to add 1. And because R is our denominator, we can just refer to that plus 1 as an R. And then that would equal P1, power to CV over R, multiplied by V1, and to the CV plus R over R. And if you can notice, every single one of our, what would you call these? Whatever, every single one of our pressure and our volumes have an R in them. So what we're going to do is we're going to multiply them, or take them to the R power, in which I'm going to rewrite over here real quick. That way I can be more into the frame. So we would have P2 to the CV times V2 to the CV plus R, I believe. Yeah, so the CV plus R, because that would cancel, to the CV plus R equals P1 to the V1, forgot to add CV, to the CV plus R. Okay, and then from here, we're going to designate that CV plus R equals CP. So we would have P2 CV multiplied by V2 of CP equals P1 of CV multiplied by V1 of CP. And from here, we are going to multiply all this again by 1 over CP, which would end up giving us P2 of CV over CP multiplied by V2 equals the pressure times CV over CP multiplied by V1. Okay? So I realized that I skipped a step when talking about what CV plus R equals CP is, and I'm going to go over that real quick. So it actually starts from entropy. So that is H, which equals U plus PV. However, we don't like using PV. And we've known from our equation over here that for an ideal gas, which everything here is that PV equals RT. So we are going to write that as PV equals RT, or equals RT. And this is per change in temperature, so we're going to do dT. And now we're going to derive this with respect to dt. And so what we would get is we would get dH over dt equals du over dt plus r, as t and dt would take the derivative of a constant times 1 equals r. And from what we know, from what we've known from earlier, is that du over dt equals cv. And with that being r, we can use dH over dt, and we can set that equal to Cp. And this is also known as the heat capacity ratio, which is important and more in thermodynamic aspects. So I caught another mistake of mine, and what I did is I multiplied by 1 over Cp when I should have multiplied by 1 over Cv to the power of. So we're going to set the Cv over here which would then make the powers be on the volume, which has an interesting effect. So we would then have Cp over Cv on the volume, Cv. And something that is interesting, once you go through all of this and you write it all out and you start testing different pressures and volumes, you find that this is a constant. That so the pressure of P2 and V2 raised to the Cp over Cv would equal P1 times V1 over Cp over Cv. So it's a constant. And so we can write that as such, and I'll do that over here. So we would have PV of Cp over Cv equals a constant, which we are going to call C. And what we know from volume is that volume equals RT over P, because it's still an ideal gas. So we would have pressure multiplied by, what did I just say? Yeah, RT over P to the Cp divided by Cv. And with the pressure over here, this still equals a constant, okay? This would be 1 minus, and we're going to actually write, because we're lazy, that's what people are, so Cp over Cv, it equals K, because why not? So what we have here would be P to the 1 minus, as we're going to be losing a power, 1 minus K, okay? And then we are going to take the R to the other side, in which we would then have then T to the K equals C. And we want to have T alternate, which would then mean we would take P to the other side, so we would have to take this to the other side, so that would be the reciprocal, be T to the P of K minus 1, and then to get rid of this K power, we would divide by K, all while this is a constant C. Okay, and from there, sorry about that, and we would then have T1 equals P to the K minus 1 over K, multiplied by the constant, and we would then separate the constant into the constant equals T1 times P of K, no, not multiply, it would be divide, sorry about that, over P, K minus 1 over K, all right, which would then give us T equals T1 times P over P1, which we would then do K minus 1 to the K. And that's it.